This conference will now be recorded. This conference will now be recorded.
Very good evening, students. Today we'll be finishing this chapter, alternating current. So today we'll discuss about the transformer, and we'll try to solve few numerical problems on transformer and related concepts. So let us start with our discussions today. So what is a transformer? You might be knowing from the very common sense of our various electrical devices nowadays being used, where transformer is used. Basically, while transmitting the electrical power from one place to another, there is a place where big transformer is being kept to step down the voltage of the transformer. Okay, so this is very common, and you might be at least familiar with the term transformer. Okay, so what is a transformer? It is actually an electrical device which is used to convert alternating current at low voltage into the high voltage, or vice versa. That means, suppose you have input, okay, input low voltage, if you wish to get high voltage, you have to pass through the transformer. It is transformer T, so you get output voltage, which is actually high output voltage. Okay, this is at high output voltage. So, or vice versa, you can do the other things also, like you have a high voltage input. If you wish to make it to low voltage, you have to pass through the transformer. So this is the primary job of the transformer. Okay, it is the primary use of the transformer. Okay, low voltage signal can be converted into high voltage, or high voltage signal can be converted into low voltage signal. Okay, so depending on this performance or this operation, whether you are using the transformer to convert a low voltage to high voltage or high voltage to low voltage, it has got name. See, step up transformer, when a transformer is used to convert input voltage, in fact low input voltage, into higher output voltage, then the transformer is called step up transformer. So basically there are according to the operation, there are two types of transformers. One is step up transformer, and another one is actually step down transformer. Step down transformer, when a transformer is used to convert input, in fact I should say low input voltage into, sorry, low to high, and here I should write high input voltage into a low output voltage, then the transformer is called step down transformer. So basically there are two types of transformers. One is step up, another one is step down. Okay, so what is the working principle? How to select on which principle it works? See, in the EMI chapter, EMI means electromagnetic induction. In this chapter, we have learned one thing called mutual induction. I hope you remember this, mutual induction. So what is this induction? First of all, I'll just recap for you. I know you know this, Still, I'll just tell you few words about this mutual induction. Before that, let me tell you what is induction at all. So what is induction? Induction is actually induction from induced word is actually mean, or induction means electromagnetic induction means if you have a coil, and suppose it is connected with a battery, okay, such that current is passing through this. Okay, if this is, so let us say this battery is some alternating battery, so that the current in this is changing by direction and magnitude. Okay, so when current changes in one coil, so in this itself, see, whenever there is a current passing through the coil, there will be magnetic field around the coil. Okay, you know that there will be magnetic field, and the field lines will be actually passing through the coil, right? Passing through the coil. So field lines will be passing through the coil, right? Like this. Field lines will be passing through the coil. If that happens, that means there is a flux linked with the coil. So this is actually self-induction. This is called self-induction. Okay. But suppose you have two coils side by side. Okay. With this, simply a galvanometer is connected. Okay, to just detect the current. We have already discussed this. So when the current is changing, like current changes to this coil, there will be a current, induced current here. Okay, induced current here. You will see deflection in the galvanometer. That means when current changes in one coil, there will be induced EMF in the other coil. So this is actually mutual induction, or vice versa. If the current changes in this coil, then EMF will be induced in this coil. Okay, so what I'm trying to say, if there are two coils side by side, when an alternating current is passed through one coil, then there will be an induced EMF in the other coil. That is actually mutual induction. So working principle of transformer is actually the mutual inductance. Sorry, induction, mutual induction. The transformer works on the principle of mutual induction. So there must be two coils here also in the transformer. In one coil we will be passing alternating current, and there will be flux link in the other coil. Okay, sorry, flux EMF will be induced in the other coil. Okay, so when a time varying current passes through one coil or one of the inductive coupled coils, an induced EMF sets off in the other coil. So transformer works on the principle of mutual induction, that is, when a time varying current passes through one coil, actually these two coils must be inductively coupled. So when a time varying current passes through one of the two inductive coupled coils, an induced EMF sets up in the other coil. So this is the thing. This is principle, working principle. Okay. Now we'll see what is the construction. What is the construction? Construction means what is this made of and how it is made of. Okay, or how is the construction, or what is the procedure of making the transformer. So this is a kind of schematic diagram, as you see here, this is actually iron core, as it is written here, iron core. This one, okay, this is an iron core, and you look here, there are coils of wire. These are actually insulated copper wire. These are insulated copper wire. Insulated copper wire. These are insulated copper wire. Okay, and here also there are coils, insulated coils of insulated copper wire. And you look this one. This is actually symbolic representation of transformer. Okay, you look, this is, there are two coils like this coil, and this is this means this is actually transformer, symbolic representation of transformer. We written transformer symbol, we will write symbolic representation, or circuit diagram you can say. Symbolic representation of transformer. Okay, so I have explained the figure. Now I'll tell you what is the construction. So transformer actually consists of two coils. As we have discussed that transformer works on the principle of mutual induction. So there must be two coils. So here, see, there are two coils. It consists of two coils of two insulated copper wires. So it consists of two coils of insulated copper wire wound on the same soft iron core. Wound on the same soft iron core. See, so this is actually core. You know, like we have discussed solenoid, right? So solenoid is actually coils of a large number of turns of insulated copper, right? And see, to increase the strength, we pass, or we actually wound this wire over a soft iron core, right? So similarly here, actually, see, there are two coils of insulated copper wire, and the coils are actually wound on the same soft iron core. This is actually very, very interesting. Actually, the two coils are wound on the same soft iron core. Okay, you look, this is the core, and this is, so it is actually electrically these two are actually not directly connected, but they are somehow connected. Okay, you can see that. So this is one core, this is one arm of the core arm, these are arms. So this is one arm, and this is another arm, arm of the core. So there are two arms of the core. Okay, and see, the coils here are named differently. We'll just discuss that. So I think I'll just erase these things what I have written. I'll just keep the original one. Okay, so this is the thing now. So there are two coils, you have understood now those things, and both the coils are wound on the same iron core. See, among these two coils, one coil will be connected to the AC mains. Okay, AC mains. So that particular coil is called primary coil. And the other coil is actually called secondary coil. And generally, secondary coil is connected to the circuit connected to the appliances. Secondary terminals or secondary coil is actually connected. Terminals of the secondary coil is connected to the output, that means to the appliances. So this side there will be appliances connected, and this side source will be connected. Okay, source is here AC mains. Okay, so AC mains will be connected to the primary, okay, primary coil, and appliances will be connected to the secondary coil. In fact, you can say the primary coil to be the input, and secondary coil you can say output. So what happens here? Whenever there is an alternating current passes through the primary coil, as you know, there will be back EMF or self-induced EMF that is there. First thing is that there will be magnetic field around the coil, and that magnetic field lines will be passing through the coil. That means there is a flux linked with the coil. So whenever there is a change in the current, so whenever you have a coil of wire and there is alternating current passing through this, then actually there will be flux linked, okay, flux linked with the coil, and that flux changes since the current is changing because the AC mains you have supplied to the primary. So there will be flux linked with the coil, and that linked flux will change with the current. Okay, that means current is varying with time. At the same time, the the flux linked with the primary coil will also change. Because of that flux changes, because of the change in the flux in the primary coil, there will be induced EMF, that is called back EMF. And since this primary coil is actually magnetically connected, since both the coils are connected to the same core, the same flux will be linked with the secondary coil. Same flux, the flux which is actually linked with the primary coil will be linked with the secondary coil as well. And whatever changes will be there in the linked flux in the primary coil, there will be change in the flux in the secondary coil also. And because of this change in the flux, there will be induced EMF in the secondary coil. That means the secondary coil will now produce electricity, or it will pass current, or it will be driving current to the circuit. So this is the construction. So what I said, in the primary coil there will be AC source connected, and whenever there is a change in the current, whenever means there will be change in the current, because AC means alternating. So since there is a change in the current, there will be flux linked with the coil, and that flux also will change with the time. So there will be back EMF EMF induced in the primary coil, and in the secondary coil there will be also an induced EMF due to the induction, mutual induction, okay, between the primary and secondary coil. Okay, so now we will see there are two types of transformer. See, types of transformer, there are two types of transformer. One is core type transformer, another one is cell type transformer. You know, cell means what? Core. Cell means, you know, which will be core cell actually. See, cell generally we say something is inside, okay, something is inside, and that is actually covered by something else. So that is cell, okay, that is cell. So if you just think in that way. Say cell type transformer is the one where secondary coil and primary coil both are actually wound over one another. First, suppose I have, see, this is the one, so I have actually, see, two arms were there and there is a common arm here. There is a common arm. So these two arms are not being used in the cell type. The common arm is used first. Suppose the coil is actually wound, the primary coil may be wound, okay, and then on over that the secondary coils also will be on, okay. So first the primary windings will be given, then the secondary windings will be given, and there will be terminals for, see, for the primary, and there will be terminals for secondary also, okay. So through this primary, suppose this is primary terminals, okay, so these are primary terminals. So the primary terminals will be connected with the AC mains, okay, and secondary terminals will be connected to the appliances. All right. So when secondary secondary coils are wound over the primary coil, then that means windings are given over the same arm, then it is called cell type. See, this is called core type. There are two different arms where the secondary and primary windings were given, okay. See, primary windings are given this arm, and secondary windings are made on the other arm. So this is actually called core type. You know, in general, high voltage applications are like wherever there is high voltage applications, then this core type transformer is being used, okay. So where there are two separate limbs or two separate arms, where the secondary and primary coils are wound on the separate arms, and in the cell type there is a single arm, primary and secondary coils are wound on top of each other. Generally low voltage applications are wherever there are low voltage applications, these cell type transformers are being used. Okay, now we'll discuss about the underlying theory of transformer. So what is the underlying theory of transformer? So before we go for discussing the underlying theory, we have to make some assumptions. One is that assumptions. First assumption is that resistance of the primary coil is very low. Resistance of the primary coil, P coil, is negligible. Okay. The second one is no leakage of flux. No leakage of flux. Okay. And third one is that secondary terminals of the secondary coil terminals of the secondary coil are open. So these are three assumptions. I'll let you know whenever there are applications of these assumptions. Okay, so what is done here? As you know, let me get this figure here. Sorry, let me get this figure. Let me get it here. So what is happening here? Suppose there are NP, number of turns in the primary. Number of turns in primary coil is NP. Okay, current through primary coil is IP, as you see here. Similarly, number of turns in the secondary are NS, and current through the windings of the secondary is IS. Okay, so when the flux linked in the primary coil changes, okay, flux linked in the primary coil also will change, and that will induce an EMF that is called back EMF. Or so I'll say back EMF in the back EMF in primary. In primary is suppose EP, and you know, if the flux link in the both, so since there is no leakage of the flux, that means 100% coupling is there. Okay, so if there is phi flux linked in this, phi will be linked in this also. Okay, so this is called 100% coupling, and there is no leakage. This is when flux linked with both the coil are same, that is actually called 100% efficiency of the transformer. So there are NP number of turns, okay, in the primary. So there will be total flux how much? So this flux is actually linked with each turn, okay, or each coil. Sorry, not each coil, each turn. Okay, each turn. So there are NP number of turns. So d phi according to Faraday's law of induction. This is the back EMF in, okay, back EMF in primary. Now induced EMF in secondary. Induced EMF. Induced EMF in the secondary. In the secondary is how much? Let us say that is ES, and that is given by NS d phi by dt. Now one thing is that when there is very less or negligible internal resistance in the cell, you look, we have already discussed this. Suppose there is a cell, I'm sorry, there is a cell, suppose this is positive terminal, this is negative terminal N, and if there is very negligible internal resistance, then if we connect this with some out some appliances or external resistance R, then the EMF across the terminals, open terminals, is E will be equal to V. Okay, because the internal resistance is negligible. Okay, if that is the case, then we can actually directly write this V EP to be VP, and that is equal to minus NP d phi dt. Okay, and this ES we can write as VS minus NS d phi dt. Okay, so these are two equations. We'll just go to the next page and write them out here. So VP is equal to minus NP d phi dt, and Vs is equal to NS d phi dt. Okay, now if we give number to these equations, taking ratio Vp by Vs, what we get? See, these are actually d phi with dt, these are actually same, so we get actually Np by Ns. Okay, this is actually having a direct relationship with the Vp is directly proportional to the Np, and Vs is directly proportional to Ns. Okay, so this is suppose equation number 3. Now, since we have assumed that there is no leakage of the flask and the efficiency is 100% of the transformer, then in case of 100% efficiency, let me give this for 100% efficiency, ideal case efficiency. That means I'll tell you what is efficiency. I'll tell you after some time what is efficiency. So if the efficiency is 100%, that means whatever input is given, input power is given, the same output power will be induced in the secondary. Okay, so that is actually 100% efficiency. So I'll write, since efficiency, let us write efficiency is actually denoted by eta. Let me first write this. Since eta is 100%, that means efficiency is 100%. That means, you know, like input is equal to input power is equal to output power. That is what is 100% efficiency. Output power. All right. So when the efficiency is 100%, then we can write VPIP, input power, is equal to the output power or secondary power. Primary power equal to secondary power. Okay, so from here, let us take the ratio of Vp by Vs. So this means what? Oh, I have written wrong here. So Vs Is. So this I can write Is by Ip. See, this has actually V voltage is inversely proportional to Ip. Look, this inversely proportional. Okay, so voltages in the primary and secondary, they are inversely proportional to the current in the respective coils. Okay, and if we just combine, so we'll just combine this equation. Suppose this is equation number 4. Now let us combine this 3 and 4. What we get? Vp by Vs is equal to Is by Ip, and that is equal to Np by Ns. So this is actually my relationship between the, like among the voltage, number of turns and current in the respective coils. Okay, so what what is inferred by this equation, let us see. See what we get finally. We get Vp by Vs is equal to Np by Ns. This is one thing, and the second thing is Is by Ip. Okay, so let me first take these two parts. Okay, this relation. So suppose I have some high output voltage, sorry, input voltage, high input. Okay, input. I want to get, I'm using transformer here. Okay, transformer. I'm using transformer here. Okay, so I'm just feeding this input to the transformer. I want to get low output, and here output in the sense these are actually voltages. In terms of voltage, I get. So if I want to get this, look what I should do. So I have to see, just by manipulating or just by altering the number of turns in the primary or secondary, we can actually make a step up transformer or step down transformer. This is like step down transformer. Okay, so in the step down transformer, what we have to do, see, I need to get Vs is equal to Ns by Np into Vp. So this value is fixed. Okay, I need to get less than Vp, Vs less than Vp. So then I should actually, Vs is less than Vp, I should get, that means I have to make number of turns this greater than Ns. Okay, so step down, this is the condition. So Np must be greater than Ns for step down transformer. So suppose we want to have step up transformer. High input. So I have low input now. I want to get it low input, right? So low input. So I want to have high output. I want to have high output. So high output voltage I have to get, that means, you know, this is actually step up transformer, as we have discussed, step up transformer, right? Step up transformer. And see, from here itself we want to see I actually see for step up transformer, my secondary number of secondary turns must be much greater than Ns, must be greater than Np. Then only this is possible. So number of turns in the secondary, if we increase compared to the number of turns in the primary, then we get step up transformer. And if we want to have step down transformer, then we have to have less number of turns in the secondary compared to the primary. Okay, now see if suppose we want to have, since in the step up transformer, what is done? Step up transformer Ns is made much larger than Ns, right? Sorry, Ns is made much larger than NP. So in that case, you look this relationship. You now look the relationship between the current and this number of turns. So if we increase the number of turns in the secondary, the number of current will actually decrease. Sorry, amount of the current or the secondary current will be decreased. So in this case, actually, secondary current will be less than the primary current. Okay. So in the step of transformer, secondary or output current is less than the input current. So output current is actually less than the input current. And in case of step down transformer, since the number of turns in the primary is greater, you look this, the secondary here, the current in the secondary coil will be greater than or larger than the primary current. So this is all about the theory part. Okay. Now what we do, we will actually see what is okay. Efficiency I have told already. So efficiency is efficiency of transformer, CNC of a transformer. It is output power or power output power I should say, output power divided by input power into 100. This will give you the percentage of this efficiency of a transformer. Okay, so 100% means input and output power are the same. Okay, so this is efficiency. Now I'll tell you why this 100% efficiency is not possible. So in practice, ideally transformers are having 100% efficiency, but practically transformers are having efficiency less than 100%. Okay, this is obvious. Okay, practically it is not possible. Why not possible? Why? Not possible. This is actually a very good question. Why 100%? This is a very practical question. Why is this 100% efficiency is not possible for a transformer? This is because there is somewhere loss in the energy, right? There is somewhere loss, or there are sources of loss. Okay, so 100% efficiency of a transformer is not possible because there are sources of energy loss There are sources of energy loss. What are the sources? Sources are actually, see, the main sources are like this. So there may be many other. So main sources are hysteresis loss. We have already discussed what is this hysteresis loss. This is actually magnetic hysteresis loss, because the core material is actually the magnetic material, right? So magnetic hysteresis loss is one source. And eddy current also we have already discussed. Eddy current loss will be there. Eddy current loss in the core. Eddy current loss. Okay. Then third energy loss is happening through copper loss. That means copper wire will be getting heated. So due to Joule heat loss, there will be energy loss. Okay. There are many other. The fourth point is there is something called, okay, we have discussed this, flux leakage. Flux leakage, what is this? That means suppose you have primary coil and you have secondary coil here. The number of number of flux passing through the primary, if the same number of flux are linked with the secondary, then there is no loss. But suppose there are some flux, they are connected to the primary, but that those flux are not linked to the secondary coil, then there is a flux leakage. See this one and this one, these are not going through the secondary, then there is a leakage. This is called flux leakage, and due to this there is a loss in the energy, and then 100% efficiency is not possible. And there is another called due to striction, magnetostriction. Okay, striction means change in the shape and size. Because of that, there will be some humming sound. Okay, humming sound, and due to this humming sound, humming loss, it is called humming loss. Due to this humming sound, there will be loss in the energy. So due to these sources of losses in the energy, transformer, a practical transformer cannot have 100% efficiency. Okay, so I think I'll stop it here for today with this. In the next class, we'll discuss some numerical problems related to transformer, and then we'll go to the next chapter, electromagnetic wave. Okay, so thank you for your patience. Bye for today.